get food in a little bit. We'll get food in a little bit. Okay? You come lay down. You come lay down. No? You lay down, buddy. I guess I can't change the title. Okay. Hmm.
binary lifting, but probably not. I'm thinking it's going to use probably a segment tree. And then maybe you could do like a binary index tree or a sparse table, but because I'm thinking, so what if you go backwards and you parse by each node, each index, and you say, okay, from here, what's the furthest out I can go? Or not what's the furthest out I can go. What's the cost for everything after this point? And then you put that, I'm thinking you might even be able to do some sort of weird like sorted intervals with a monotonic stack. It's one jump from I to anything between I plus 1 and AI, two jumps from I to anything between AI plus 1 and max AI plus 1 and AI. Max AI plus 1 and AI. Two jumps to anything between AI plus 1. So if we have I here and we're saying, okay, this is AI. That's like what this index is. You could jump here. Anything from... Oh, A at I. I see, okay. Yeah. And then the next jump could be anything from here to the array ends, but like the next thing, which would be A at I. Yeah, I see how your mind would go to binary lifting because this kind of recursive structure feels very binary lifting-y. I guess I'm thinking what you could do is you could encode this as, you know that all of these, the cost for these are going to be 1, and you know that you're going to jump to one of these in order to get every single cost after this. There's no reason why you would ever, if you jumped from I to, let's say, here, had some crazy range that you really wanted to go to, there's no reason why for any other thing you could possibly ever want to go to, you would jump to like there or there. So I'm thinking what it's going to come down to is for every f of I, I'm not going to go with this. This doesn't matter. I'll come back to this if I really am like starved for ideas, but this will go way over here. Or just DP maybe. I think it's going to be some sort of like going backwards DP where you have to like build out a range query data structure like as you go backwards. So for any f of I, there's really two parts to it. There's A at I minus I, just straight up, because you're saying for everything in here, I can, it takes me exactly one jump to get there. So then you've handled that, plus the difficult part, which is everything after that. But I think if you're smart about it, you could query this range and say everything in here has some cost, which is itself going to be this value plus, let's say this is the optimal value, plus this range. So if you had a way to have this range not represent f of I, but like let's say g of I, f of idx of max between I plus 1 and A at I. A at I minus that index. Yeah. Although I'm thinking it's tricky because you could have a scenario where like up here, if you had, let's call them I, this will be J, the optimal J that you want to go to, and A at I. So you can look at anything in this, you can look at anything in this range. You want to jump to here, and then this goes to something else. But, this is important because I was going to say, what if this didn't reach there? What if that didn't reach to A at I? But that's actually not true. It always, if there were any J at I where you couldn't reach A at I, I'm thinking like that would be really problematic, because then you can't just encode this to like, well, what do you want to search for the maximum of? It's going to be something like f of j minus j, because you're going to say like, well, it costs this much. That's great. But then also there's this like, these things I've already accounted for that I can just immediately jump to. I don't want to jump twice if I can jump once. J is supposed to be optimal. It's the max value of the range. Or maybe this is plus j, I don't know. But you're looking for some sort of minimal, well, would it be plus j or minus j? You're trying to say, what's the j that has the lowest cost? The further backwards it is, the more you take away, and the higher cost it will have. So yeah, it's f of j minus j. You're saying if you have some, let's go back here for a second. If you had some, let's say J1 and J2 that had some series of costs associated with them, J2 is potentially going to be preferable. In case of a tie, or also like, let's say J2 reached to here and J1 reached to here, and like f of J2 was equal to f of J1 plus 3. But then there were two values here that it could immediately jump to. Or let's say plus 1, sorry. There were two values here it could jump to, but you can already reach those. So as far as jumping to J2, as opposed to jumping to J1, you would always want to jump to J2, because then you can jump further in one go. So I'm thinking like f of j minus j would be the encoding. But as I'm saying this, I think I'm overthinking it, and I think you could devise a greedy formulation and just say whatever can jump the furthest is necessarily going to be the best option, right? So then you just say like f of, if you have some range, you don't even bother trying to encode this in some special way. You just say get the minimum in this range, or the maximum in this range. This is my Python pseudocode coming out. You just say this, where g of I is equal to how far I can jump. I mean, that's a little bit of a convoluted way of putting it, but you just jump to the thing that can jump the furthest, because it will always, like, when's a world where you have like, this is A, you're at I, and you have like J1 and J2. This can jump to there, this can jump to there, you can reach both of them. When is a world where you would ever choose that? You just never would, because any option that's available to J1 will also be available to J2. So I think you could do it this way as well, but I think it's unnecessary, and I think you can just go off of this. So with that in mind, you say, okay, go backwards, build the DP out. I feel like you could build a sparse table as you go. It would be kind of weird, but you would have O of 1 queries. No, you don't even need to do that. You just build the sparse table at the start. You just say, what's the maximum of everything in this range? Just straight up, like the maximum value in A for everything in this range. And then you iterate backwards and you say, it's going to be, let's say J2 is the maximum. So it's going to be J2 minus I. J2 plus 1 minus I. Yeah, exactly. J is max of A at I plus 1 all the way. Yeah. It's going to be J2 plus 1 minus I. And then for the sake of like illustration, times 1, because it takes you one step to get to any I plus 1, I plus 2, all the way up to J2 itself. No, it'll just be J2 minus I. Because you're inclusive of J2, but you're exclusive of I itself. So it's kind of pointless. And then it would be dp at J2. Okay, that's like... I think I did a pretty good job of proving this to myself. Slash to Solaris. But my final question is if this is gonna... Here we go. This is a little calmer. My first thunderstorm with my dog, he was so scared, and I played this album really loud, and it helped calm him down. Okay, I'm practicing proving correctness more rigorously. So I wanna practice that here. So we have the optimal solution, because I am kind of doing something greedy here. I'm saying greedily you always want to jump to the thing that can jump the furthest. Do I care about that? Is that worth trying to do? I'm saying the optimal solution is the cheapest cost per I. The greedy solution is that it will be yeah, and I think it's I'm happy with the level of proof I have, the level of rigor, but I think there's one additional thing that I actually think is easy to overlook, but it's pretty like subtle, and it's that for any j greater than I, there will be some j that you can reach from I that can reach outside the bounds of A at I. Like there will be some j that is greater than I. Let me write that the other way. J is greater than I. J is less than or equal to A at I. And A at J is greater than A at I. Right? I think a better way to write this actually is not that this will always be the case. It's if there is any, there will always be, to the extent that there is a j within I's range, there's at least one that has that. Because you can reach the final I, in which case there's literally just no j. All right. Let's write this bad boy out. Trains and statistic, I already kind of started writing it out. But I think this is kind of down the toilet. I was going for something else, so I think I'm going to say this is going to be dp A at I equals x. Don't need to sort it anymore. Am I printing res? No, I'm got the sum. So in the end, I'm going to say something like, I think I can say accumulate dp plus n 0 ll. That ll is really important. That always messes me up. Okay, that's what the end is going to be. I think I just need to say dp at n minus 1 is equal to 0. It always costs nothing to jump from the final thing to itself. There's no j you can jump to, so it doesn't really matter. If I look at this, it should say all of these can reach the end. Right, so this costs 0, this costs 1. I actually don't see why this wouldn't be 3. I feel like there's some sort of doubling going on. For the first sample, it's possible to get from any station to any other with greater index only using one ticket. The total number of pairs is 6, so the answer is also 6. Why would it not be 3? Only tickets to stations I plus 1 to A at I inclusive. Like, what does it mean? Do you just multiply everything by 2? Is that clearly not if the answer here is odd? But why would this not just be, if you have 3 values, and all of them can reach the end, why would it not be 1, 2, 3? It sounds like it's also saying like 4, 5, 6, but it seems to specify among all pairs 1 is less than or equal to I is less than J is less than or equal to N. Oh, okay. It's that there's a 4th node that isn't shown because N is 4. It's saying I'm not even going to give you the 4th number because no ticket, it's like, it doesn't matter. It's only a destination. So really, okay. So what it really is not this. It's this. And then it does hold. It's just like 1, 2, 3, 4, 5, 6. Okay, perfect. So this is dp at n minus 1. This should be minus 1. So you input 4, you say, okay, this is just 0. Their costs nothing. This is going to always be 1, but whatever. Before I do the DP part, I need to build the sparse table. But I think I'm going to do that after because I'm already kind of thinking so much about this logic, and that's just building a sparse table over A. So I'll say for I equals n minus 2, I is greater than or equal to 0, I minus minus. J equals, well, I'm going to say int L equals I plus 1, R equals A at I plus 1. No, I'm not going to do that. That's needless. So these are the left and right bounds, but it's inclusive. So I'll say J equals sparse table dot query L R plus 1, because it's going to be exclusive when I do that. dp at I is equal to J minus I plus dp at J. You just always jump to that. Is there going to be any weird integer overflow even though I'm using longs? That always happens. Yes, there could be. Because J minus I right here, J and I are both integers. So then it's going to add a long to an integer, and then it's going to freak out and then try and convert it back into a long, but it'll be too late. So actually, just for the sake of being really careful, I'll do that. Okay, that looks good. Now to build a quick sparse table. N. I'm going to have the constructor take... Wait, is that the right way to do that? No, I'm back in Python world. Struct sparse table. Private, public. Int query L and R. Okay, we got that. That looks good. So what am I actually doing here? I could have a vector of vectors, or I could just have the sparse table kind of be like a wrapper structure that doesn't actually really hold anything, because I'm kind of dubious of how it will store that in memory. And I just have a 2D array here. I just have a 2D, like a 2D raw array that I just like fill out every time. How big is this? Let's see. 100,000 log 2 is like what, 18 or something? Yeah, 17. Okay, so and then 17 times 100,000, it'll be like 2 million. I'm fine with that. So I think I'm just gonna block out that memory and say int table, and then this, I want it to be, yeah, this is fine. If I have like, if I had a vector and it was dynamically allocated, if it was like constantly resizing, that would be such a disaster. I don't want to do it that way. Uh-oh, wrong answer on test 4. That doesn't bode well. 1, 2, 3, need one more. And then I'll just do 20. So I want to say the level is first and then the index on that level, because that's gonna be a little nicer for memory. I don't think it really matters though. What do I actually do for the table? I mean, I guess I just clear it. Another thing I could do is just say, don't even have A, just have the table, right? Table at 0 at I equals X. Like, don't even bother. Because this you're just saying for, like, at the 0th level, you're just saying, for queries where it's a size of 1, you're just querying an individual index in A. That's the exact same thing as just A. So I think that's fine. Uh-oh. Looks good. The age-old question, do I even need to empty it out? No. Because I already, when I was taking the input, filled out the 0th layer. So all I need to do is figure out how many layers I need to go up, which I'm not even going to do any log 2 thing. I think I'm just going to say int j equals 1 for, do I even need that? I think just say int j equals 1. 1 to the j is less than or equal to n, j plus plus. So then this will go up in levels. It'll start at level 1, so it'll say you're filling out queries of size 2 and then size 4 and then so on. I want it to be less than or equal to n, which feels a little weird, but like if n was 4, for example, you could have a query that's like exactly that. So you want it less than or equal to. Okay, and then I need for I from 0 to, I think, n plus 1 minus j. This is the individual index. So I would say for size 1, we've already handled that, doesn't matter. For size 2, you have 1, 2, 3 of them, which makes sense because like 4, if n is 4, plus 1 minus 2 equals 3. And then plus 1 minus 4 should equal 0. Should equal 1, which makes sense. So this will have 1, 2, 3 sets of 2 nodes, and this one will just have a single one. For I from 0 to n plus 1 minus j, let's see, I need to say L is equal to, I don't care about LLs, at least it can be an int. L is equal to table at j minus 1 at j, at I, sorry, R is equal to table at j minus 1 at I plus 1 to the j minus 1. So it's like if you were trying to parse like the fourth thing, you'd say, okay, well, I need to have the minimum of that and that. So this would be just starting at the same spot, but half as large. And then this one would be starting halfway up. Looks good. And then table at I is equal to max of L and R. Table at J at I. Wrong answer on test 4. That's ominous. Okay, that looks pretty good. Okay, query. I just need to say int size is equal to R minus L. So if you said from indices 0 to 4 exclusive, that's what I care about, you'd say size is 4. I guess I'll just say like int j equals 0 while 1 to the j is less than size, something like that. J goes up. I actually want to say less than or equal to size. And then it goes down. So this is going to be the largest thing less than or equal to the size. Then it's pretty simple. I think I just say return the minimum of A at J at L and A at J at R plus 1 minus 1 to the L, I think, or 1 to the J. So for example, if I had like a bunch of random stuff, let's say L equals 3 and R equals 4, 5, 6, 7, 8. So I'm saying I want the minimum of everything in this range. It'll say, okay, J goes up to 2. So it's a length of 4. And then I say, okay, well, you just want like table at 2 at 3. And then you would want also the min of that and this. Oops. So table at 2 at, my logic is it says 8. I think because it's exclusive, it's just 8 minus 4. So 2 at 4. So there's no plus 1. Okay, the sparse table is built. Oh, except A doesn't mean anything. I could just rename table to A, whatever. We got table. Let's see what this comes up with. One. You love to see it. Four, -1, -2, 0. Very odd. I mean, what is it even coming up with here? It said 2 leads to 0, 1 leads to 0, 0 leads to 4. I think the problem is that I'm going out of bounds. So right here, when I say R equals table at 0 at I, AC, nice. I can just say like min of n and that. I think that kind of solves that. Except it should be n minus 1 because I made R here exclusive. So it says 2 leads to 0, which is not right. So this is not doing the right thing. These are too high by a single value, but I can deal with that later. 2 leads to 0. Hey, Vortism. So it said L and R here are both 3. I see. I think the problem is that it's going out of bounds still. The problem is that it's still thinking about, like, the way that this is working is if there are 4 elements here, all of these can jump to something, a number of things. But I'm still considering them to evaluate to being able to jump to here. And then because it's like, well, I can jump all the way to the final element, it's trying to evaluate the final element in the sparse table, but because this is the final element and it's not really jumping to anything, everything's kind of falling apart. I think a really easy fix would just be to say, okay, fine, then this jumps to infinity. And then that's pretty jank, but I think everything else will just say, okay, well then always jump to that, and then problem solved. Because in theory, I mean, this does jump to, like, beyond what anything else can jump to. So I could just say table at 0 at n-1 is equal to... Is there any rule that everything has to be less than or equal to n? A at I is less than or equal to n. So I guess I could just say n plus 1. Like, all, and this just designates always jump to the end if you can. And then the end is specifically, like, where it jumps to, which is nothing, is specifically counted as a corner case. Okay, 3, 3. Let's see what these are actually coming up with. Div 2e nowadays is way harder, yeah. Let's see. 3, 3. This says jump to 5. Okay, I think I see the problem. The problem is that it's querying... It's kind of like, I'm saying jump to the thing that can jump the furthest, but then what I'm querying is what's the furthest you can jump to from anything here. But I don't actually want that value. I want literally the index that has that value. So I guess I could say, I think I'm just going to bring back A. A at I is X. And then I think table at 0 at I is just going to be I. I'm just going to say these now represent, like, yeah, the indices themselves rather than the minimum, like the values of those indices. And then I guess that's n. Damn, that's getting convoluted. I need to think about that for a second. I could just have the table be a table of pairs too. That way it will compare by indices. I think there's one more thing I have to account for. So let's say you're at I and you're trying to jump to either J1, you've decided, or J2. You can jump to either of these. They both go to the same spot. Which one do you jump to? According to my logic, it doesn't matter, they're both fine. But wouldn't you jump to J2? Because J1's going to jump to J2. So that's costing you an extra step compared to if you just jumped to J2. That's where I'm like, this minus J thing comes in, but I feel like I was so confident that this works that I'm starting to question myself a bunch now that there's like a pretty basic issue with my sparse table. Let's see, we got the sparse table, that was fine. Here I was saying there's some J that can jump beyond I's range. Yeah, no, I'm not overthinking it, but there is one more step, which is, let's say, where was I? Up here. And I'll actually be pretty like large scale with this. So if you have this, these can both jump to the exact same point. Let's say over here. And I is able to jump from here to like here. So you're not actually saying like even for everything past here, jump to that. The whole point of there's some J such that A at J is greater than A at I in this range. The whole point of that is just to say for all these, it's an extremely predictable amount you can decrease it by. So you do always want to jump to one of these, and it doesn't really matter as long as the next thing you do is outside here. So you just need to take this away and then you're good. And you know that that costs 1 with J, and it costs 1 with I. So therefore you're taking away A at I minus J. Because if A at I is like here, or if A at I was like exactly here, J was the last thing you could jump to, then anything J can jump to was outside of your range, so you don't want to take it away, there's no overlap. But if it was here, you'd say there's 1, 2, 3, 4 things that this is going to spend 1 jumping to that you don't need to, that you can already jump to from I. So that's kind of a little detail. Which problem are we doing? It should be pinned still. It's some old, I'm kind of practicing like, in my mind, like DP problems where you need to create some sort of data structure. Like segment tree DP, I guess you could say. J is that, so DP at I is DP at J plus that minus A at I minus DP at J. I'll just be really paranoid with my LLs. Okay, that looks good. Now I need to actually fix the problem with the sparse table. So the problem is that it's recording the values, not the indices. That's like not that bad of a fix. I think max, it must have a custom comparator, right? Yeah. So I can say int J1, int J2, return A at J1 is less than A at J2. Table at I is that. Okay, and then here, it's the same thing. Except I don't know why the hell I'm saying min. I want max still, right? I'm saying you're jumping to the furthest thing. Do I care about that at all? That's so unreadable, I feel like. I would rather just say table at j at I is equal to a at j1 is greater than a at j2, question mark, or L and R. L or else R. That makes a lot more sense to me. And then it's going to be really similar here. J is 0. I guess I can call these I1 and I2. R minus 1 to the j. Yeah. It's greater than a at I2. I1 or else I2. Okay, that should fix that problem, although not quite, because I set a at I to be the right thing. Table at 0 at I should just be I itself. Now the last thing that's like kind of annoying is n minus 1. I think I can say table at 0 at n minus 1 is that. A at n minus 1 is equal to n plus 1. So just say like that leaps after the end, and then that should be fine. Okay, what does this come up with? Comes up with nothing. Oops. L is 3, R is 2. I think it's because I changed table. So this should just be A at I now. 3 and 3, 2 and 3, 1 and 3. That's kind of what I want to see. Uh-oh. It says everything is 8, which doesn't seem right. Table at j minus 1 at I. For real? Two, 3. Okay, those look like normal values to me. Notably, none of them are 8. So why would this come up as 8? Oh, no, I said A at J. I want table at 0. Table at J, not A at J. One, two, three, 3. That sounds right. Hey, smart coder. Thank you. So if it's 4, 4, 4, everything should just reach 4. There's no reason why it wouldn't. And I think that's fine here. I think when it says 1, 2, 3, 3, it's saying this is the index that you would want to reach. It doesn't really matter which index is actually chosen. So this should be valid. And then this says 3, 3, 3, 3, 0. which I think is also fine, honestly. N plus 1 minus... Yeah, I think that's kind of gibberish, because this isn't j, this needs to be 1 to the j. Yeah, okay. And now this is saying you would never query anything past this, it wouldn't make sense. You would never query anything past that, it wouldn't make sense. Okay. Well, the sparse table looks pretty good now. Really could have just copy pasted a template, but what are you going to do? So where does it mess up here? It seems to not like this. Or it seems to not care now. -1, -2, -3. At least it doesn't do some weird out of bounds thing. So I'm saying you want to jump to 3, which costs nothing. It should add j minus I, which is just 1. A at I minus dp at j. This was definitely supposed to just be j. There we go. Okay. It's probably a at I plus 1 minus j. That would be my guess. Because these are all off by exactly 1. But I don't love just like guessing that without really having any rationale. So why would it say it costs 0? Because you know you have exactly 1 jump only to the next thing. So a at I is 4. J is 3. Right? Except it's 1 indexed, if I'm not mistaken. Yeah. I'm guessing a at I is less than or equal to n. Means it's 1 indexed. Which I didn't really think about. I guess I haven't done code forces in a minute. I think it doesn't really matter though. Like that doesn't really affect that much. A at I plus 1 minus j. Pretty easy fix though, which is just make it x minus 1. Right. I think that's actually going to exacerbate this problem though, so I don't know. I think that might have been incidental. No, it wasn't. Just so that now it's 0 indexed, and then everything's fine. I don't have to worry about 1 indexing. I never have to like translate it back, so that should be fine. What the hell? So this should be 2355. It's going to say something like this. So this can jump here. This can jump here. 3 can jump only to here, I think. And 2 can jump only to here. So the answer here should be 0, 1, 2, because this can jump to either of them. This is going to be jump here for anything, and then jump here for anything. So this should be 5. And this should be 9. What does this get me total? 9 plus 8, 17. I think that was the answer. Okay. So what did mine come up with? 1, 2, 3, 4. Okay. I do kind of want to know what the I and J was, though. 3, 4, 2, 4, 1, 2, 0, 1. 3, 4, 2, 4, 1, 2, 0, 1. Yeah, that's right. So I think it's all functioning properly. I think there's one more thing I need, which is, for example, when you're at 3 and you jump to 5, it didn't just cost you 1 to jump to 5 and then everything else is like the same. This didn't cost you 1. This costed you 1 per thing you do from 5. So up here, when I say, okay, we got L and R, we got J, dp at I is dp at J plus LLJ minus I plus all of A at I minus J. I think it's for everything after A at I, it actually costs 1 more. I feel like some of these terms are going to wind up canceling out, but I think that might even be overthinking it. I think it can just say I think the term that's going to cancel out is LL of J minus I. I think I can just change this to N minus I. Because no matter what, you have to dedicate a single jump to get to any... Like, the first thing you do is always going to take a single jump. Oops. Two, 3, 7, 12. God damn, really monkeying around with the code here. Okay, I guess that's what I was looking for. Well, I'm worried that breaks the previous test case in some way. No, it doesn't, because I think they all extended out of bounds anyway, so I didn't really run into that. Looks pretty good. Where would this mess up? This would mess up, in my mind, this is going to mess up when there's like a million elements to jump to, and the number quickly spirals out of control. So I'll just quickly make like a VI test. I think it's iota. Test up again, test dot end 2. Perfect. Oops. So this should be, I think, 10,000, and it doesn't really matter, but I'll just say 10,001. I think it's 10,002. What should the answer be? Some giant number around 10 to the 8th, I feel like, because it's like, well, it doesn't overflow. That's good. Yeah, this seems more right, because it's not just... It would be if only you were reaching the final thing, it would be some giant number around 10 to the 8th. I think it's some giant number around 10 to the 8th natural number. Okay, well, it doesn't overflow, so... test cases on this bad boy. Nice. That feels good. What did it rate this as? Was that candidate master or something? 2300. Okay, I already read this one, so I'm going to think about it I'm going to reread it for a second and then think about it. Okay. So you're given a grid of ones and zeros, and then you're given a series of rectangle queries. You need to query the largest square of ones that exists within that. Okay, I'll be right back. Wanna get some food? It's very warm. It's gonna be very warm. It's very hot. Okay, we're gonna keep it for a second. I'm just gonna wait for his food to cool off. Well, I see the binary search thing, so. I mean, and that is an immediate thing you could try, is just. Why would that not work? Why would you not record the largest square from each Yeah, you'd make a 2D sparse table. Record the largest square that can be drawn from each cell. So let me draw this out here. Good enough. Okay, oops. So if you have a bunch of ones and zeros, I'm just going to have them be like filled in or not filled in for now. Let's say that's filled in, that's filled in. Okay, you have something like this, let's say. So then you could just say, for each of these, what's the largest square? Where this is the top left. So this would be 1, or like, yeah, this would be like 1. This would be 2, these would all be 1, and then this would be 3. Yeah. And then if you have some rectangle query that you need, let's say like this, and it's like that, this 3x4 right here, you would just be like, take a query of everything here, see what's the largest square you can make. Except, I don't know why I said that, because it wouldn't be that, it would be binary search. See if you can make a square of a given size. And you would have to do it that way because, like, for example, if you had this, you'd say, I can make a, or even like this, you'd say, I can make a square of size 3. I know that, but I don't know where I can make that necessarily if I use a range query. And so I don't know that like that square actually even fits within my query rectangle. So you would need to binary search. And then the moment you're binary searching and you're saying, can I make a square of blank size? Then you're in a much better spot because you could say, okay, like try making a 2x2 square. If I try that, I know exactly in my, I'll do it down here so it's a little more viewable, or maybe I'll like, if you have this and you have a 2x2, if you're looking for a 2x2 square, you just know exactly, like, let's say right there, you know exactly that you're only going to be looking at if anything here is greater than or equal to 2. For a 3x3, you know you're looking at exactly if any of these can be greater than or equal to 3. So you kind of can like query the correct thing. And then it becomes a matter of implementing a 2D sparse table, which they're not that hard to implement. I don't know why this took me so long, wherever it is. This took me so long to implement. I don't know what happened there. A 2D sparse table? What would that look like? I think that's fine, right? I'm guessing it's saying, okay, the number of queries is 1,000,000. That's fine. Even if it was logarithmic, it would still be fine. N and M go up to 1,000. So N times M goes up to 1,000,000. 1,000,000 log 1,000,000 should be fine. But it's not even going to be that. It's going to be, oh no, it will be that, basically. So a sparse table of sparse tables, what's that going to look like? That's going to look like n log n across rows, just a regular sparse table, if you treated each row like a number, you're going to have a bunch of these. But then each of these, instead of being a number, are going to be its own sparse table. So it should be log n sparse tables. Okay, so it'll be n times m times log n times log m to create 2D sparse table, and then O of t to query. No, it's not going to be O of t. It's going to be O of t times log n to query. I guess if I'm getting really specific, which it actually does, it does matter. It doesn't matter for this problem, but I've seen problems where it really matters. Because if you specify min of n and m as opposed to just n and m, where like they form the dimensions of a matrix, or the side lengths of a matrix, you can do some like square root time complexity stuff that you can't do if it's just like one of them necessarily. And this should be fine. I mean, I don't know. This problem's rated 2700. A div 1D. I feel like those are at most like a what, 2300 these days, or like if that. No. Oh, really? Animals and puzzle. Okay, I clearly need more help with my sparse table implementation, so I'm just going to implement it from scratch again, but it shouldn't take nearly as long as last time. K rated. Yeah, implement a 2D sparse table. I think there's kind of a mystique around those sorts of like intermediate data structures that, from what I've noticed, older problems have a lot more reverence for, and like modern problems, they're like, whatever. Everybody and their grandma has a link to a segment tree template somewhere. Yeah, and the whole like kind of parametric search thing, I think that definitely was like more in meta, I think, back then. So we got N and M. There's not any need for LLs in this. A 1001, 1001. I could also, at the point where I know, whatever. It's going to be so much less confusing if I just keep it as the top left. I could have it be the bottom right, but I don't really want to mess with that. I equals n minus 1. I is greater than or equal to 0. I minus minus. So I want to look at three things. And I also don't care about n and m minus 1. I just immediately want to go to n and m minus 2. So if you're, let's say the matrix ended here, you're here, or no, let's say you're here. I don't care about where it ended. If you're here, how are you going to get the size of the square? I think you just need to make sure that all of these are at least that minus 1, right? So it's just the minimum of all of these plus 1. Is that right? The min of all of those. So for this to be 2, all of those have to be at least 1. Yeah, I'm going to go with that for now. Seems fine. Seems like the kind of thing that if it turns out to be wrong, which I kind of doubt, then it'll become apparent why that's wrong. If AI equals 0, continue. A at I at j equals min. I don't think, is it smart enough to know? I never figured out how to do this in C++. A at I plus 1 at j, A at I at j plus 1. That, oh, it is smart enough to do that, okay. So just get the 3 that you care about. It's going to be the min of those plus 1. So if one of those is 0, then this is going to be a 1. As far as the sparse table goes, I said it's going to be faster than the last one. However, this one's 2-dimensional, so it's not exactly the same. So what am I representing? Each row sparse table represents a series of rows, and then each column sparse table represents a series of columns within those rows. So there's really going to be 4 things I'm checking. 2 sets of columns for each row, and then there's 2 sets of rows that each query is going to check. I think I'll just go with, should I go with 20 again? Is that very smart? That's kind of big. No? I think I should go with 10. Because 10 times 10, 100, times 1,000 times 1,000, 100 million. I think that's okay. I think. I don't, how big is the memory complexity? 512, 5 seconds? Yeah, that should be fine. So it's going to be 100, the breadth of rows that you care about, and then 1,000, the sets of rows potentially, and then another 100, and then another 1,000. It's a lot of memory. Get the sparse table. For x in res, print x. Okay, this is going to be for query from 0 to t. Answer is sparse table.query x1, y1, x2, y2. x1, y1, x2, y2. x1, y1. y1 minus minus, x2 minus minus, y2 minus minus. Right, I'm going to take a wild guess and say that 1, 1, 2, 3. So it's saying 1 to 1. Yeah, these are min of 1, so. Okay. And then I just got to build the sparse table. So the 0th row is just A, although it's not that simple. It's going to be every table at 0 at I, at 0 at J. I wonder if I could do 100, 100, 1001, 1001. I think I probably could, but this makes more sense in my mind. For I, for J, table at 0 at I at 0 at J is equal to A at I at J. And then I need to do for every layer in the outer sparse table for every layer in the inner sparse table. And I think I'm actually just going to build around this. Layer 1 is equal to 0. While 1 to the layer 1 is less than or equal to n. So for every index, I'm sure there's a way to just do this recursively. But I don't, do I want to sort that out? I would just say your sparse table has a dimension and an object in that dimension. And then you're just taking like a maximum. And a comparator, like a comparison. could just name them explicitly 1D and 2D sparse table too. That's kind of an easy way around that. Yeah, I'm gonna do that. That's gonna be a lot simpler. No, it's not, because I'm using a static array. Yeah, this is okay. But I do need the base rows. I guess I could just put this here. A at I at j is x. I could also say table at 0 at I at 0 at j is equal to x. And then A barely matters anymore. Oh no, I need to do that after. Okay, we can just start this out at layer 1. No, we can't start this out at layer 1. We have to have this at layer 0, which is fine. While 2 to the layer is less than or equal to n, for every index, so build out the sparse table. I need the base case. So for all I from 0 to n, just make a sparse table across that row. What's that going to look like? For every layer in that sparse table, iterate through the indices. Okay, yeah, that's not that bad. This is layer 2 for j from 0 to m minus layer 2 plus 1 minus. Yeah, that's right. Left is equal to table at 0 at I at L2 at j, L2 minus 1 at j, R0I, but now it's not L2 minus 1. It's L2 plus, no, minus 1 at j plus 1 to the L2 minus 1. Yeah. Table at 0, at I, at L2, at j. Okay, that's every sparse table, every 1D sparse table set up for the 2D sparse table. So then I need to aggregate all the ranges of 1D sparse tables. So 1 to the L1, okay, that's fine. For I from 0, I think I need this to be plus 1. Yeah. Okay, for J from 0 to M, I think it's not time for that yet. This was before when this made more sense. I think I need to say now for L2, how thick is each column sparse table for this row sparse table? So it's going to basically be exactly the same as this. Yeah, I think this isn't bad at all. Well, is it bad? For every set of rows, dang, I think the time complexity is fine, but okay, I is the current row, L1 is the current size, L2 is the current width, J is the current X offset. So this should be L is, I don't think there's any need for J comparison anymore. I think all the J comparison is done. Right? There's no need to ever relate L2 to L2 minus 1 anymore. Yeah. You're just saying take this exact subset of L2 and J. This is at I, and then this is at I plus 1 to the L1 minus 1. And then this is table at L1 at I at L2 at J. L2 from 1 to that. Should be exactly the same as that. Okay, that should be the constructor done. X1 and Y1 and X2 and Y2. Size 1 is equal to X2 minus X1. looks like it's inclusive. So I think I'm just going to say these go down by 2. So the initial size is x2 minus x1. While L1 is less than or equal to size 1, L1 plus plus. L1 minus minus. And then I want to do the exact same thing with L2 and size 2. This is 2, 1, 3, 2. That would be 2. Of the up left rectangle, corners to the bottom right. X1 and X2 less than or equal to N. Yeah, so X is vertical here. That's fine. Here I just get the 2 indices. I return the one that's bigger. Here I'm going to have two row readings, and then I'll take the bigger of those. So at L and R minus 1 to the J. I think I'll be really explicit here. In row 1 is equal to x1. Simple enough. In row 2 is equal to x2 minus 1 to the level size 1. Do I just do the same with call? I guess I do. Call 1 is equal to y1. Call 2 is equal to y2 minus 1 to the size 2. I've got the row and column. There's going to be 4 queries that happen, and it's the maximum of all of them. X1 is equal to table at size 1 at something at size 2 at something. And then it's just the combination of these two sets. Size 1 at row 1, at size 2 at column 1, Size 1 at row 1, at size 2 at column 2, size 1 at row 2, size 2 column 1. At column 2. Okay, this is going to get the wrong answer, but that's fine. I just need to binary search this and then it's good. That's not right. Those went up instead of down twice. So what happens? You keep going smaller until you find something. And potentially you could just find a 0. Right? Yeah. So it's going to be the largest thing including 0, where you're able to create a square. x2 minus x1, y2 minus y1, while r is greater than l plus 1. The object has type qualifiers. What the fuck does that mean? So check, it could be up to that size. Exclusive. Look halfway. Look for the largest square, but it's not x1, y1. It's x1 plus 1 minus threshold. So if you had this, you were checking a threshold of 3. You'd say you keep going up until so normally it's a size of 4. So the threshold is size 3, so I don't know. 2, yeah, that's right. Okay. If it's a size of 1, that's very simple. That's just plus 1 minus 1. So you check every single square. If it's a size of 2, you're saying check up to that. Yeah. So this can only ever query up to r minus 1. So only go up to exactly the difference between y2 and y1. So if y2 and y1 were here, that's minus 2. It's checking exactly a size of 2, which is right. Oh, oops, okay. Okay, it's creating the matrix correctly. So up here, when it queries, there's an issue. Oops. Y1, X2, Y2. Zero, 0, 2, 3. Seems right. Zero, 0, 2, 3, and then it queries that and it gets nothing. And give it until 310. Why was this 100? I think this was definitely supposed to be 10. 100 makes 0 sense. L1 and L2, it said 1 and 1. That seems right, because if you're saying 1 to 1 and 2 to 3, you're saying it's here up to here. Okay, so the 4 things it should check are these 2 I and J combinations and then these 2 I and J combinations again. -2 and -5. Good boy. Size 1 is that, L1 is that. Oh, well, it's definitely L1 and L2, not size 1 and size 2. That's probably the issue. 0, 0, 0, 1. That's backwards. Right, call 1, call 2. No, that's right. Zero, 0, 0, 0. So this tells me that the indices are formatted correctly here, but that the table isn't being filled out correctly. Oh, or they're not, because this is not right. L1, 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 L2, 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 L2. Okay, did I make that mistake anywhere else? No. Okay, it gave an actual answer. It didn't give the right answer, but it gave an answer. Probably because I said min instead of max. No, so it's saying 1 for all of these. But it should recognize that right here there's a 2. And it should say that because... Oh wait, L1 is 0 now, and L2... is 1? That's very weird. Am I sure about that? I think I have so many print statements I gotta get rid of some of them. Whatever, good enough. Yeah, it is saying that. I see. So it's saying try a square size of 1. There is a square size of 1 in this little 2x3. Try a square size of 2. Right? Or is it saying try a square size of 2 and then a square size of 1? It said try a square size of 1. Okay. And then it said you're measuring this 2x3. Which means you're looking at just literally every single thing in that rectangle. Wait, am I an idiot? I think I just debugged my thing like 2 minutes ago, and this is just fine. This is doing the right thing. It's saying if you try to square size of 1, then there is this 2x2 that it picks up on, but it's outside of the range that it needs to like register. So it's fine here, and then it doesn't pick up on it here. That's actually fine. So I'm going to get rid of some of these print statements because I think it actually might be doing pretty well here. Print. No, get rid of that. Get rid of these. I'm going to be really happy if I don't. Oops. I never have to look up here again. 11022. Is that right? Yeah, I forgot to comment this out. 110. So weirdly, 1134, it gives 0. No. It's 3234. It gives 0. So that would be 1 2 3 1 2 to 3 4. No. That's right here. Why would that give 0? That's very odd. No, I can't do that. What can I do? I can just say here, if query doesn't equal 2, that's the one I care about. Continue. And then I should see just a 0. Perfect. So it should try exactly a threshold of 1. And it's trying 2, 1 to 3, 4. 2, 1. Oh no, but now it's 0 indexed. So 0, 1, 2, 1. So here it's a 3, 4. So it should look at this 1, 1, and 0. But it immediately says it's not possible. So up here, I guess I got to bring these back. It's saying 0 and 1. That's right. So what it's saying is I'm checking this 1×3 area. So it wants to look at the 0th row in the sparse table, kind of. Or it wants to look at the 0th, like, size of sparse tables, aka just representing one row. And then it wants to look at the first width of sparse tables. This is maybe a way to put that, aka representing a 1×2. And then it's going to compare this 1×2 and this 1×2. And then it's going to come up with an answer. So it should see that there's 2 1s and a 0. But it doesn't see that. So that's right. Row 1, row 2, column 1, column 2. It's saying 2, 2, 1, 2. 2, 1, 2, 2. 2, 1, what's it doing here? Yeah, it's saying 2, 1, 2, 1, 2, 2, 2, 2. So this is correct. This is correct. This is not correct. So that tells me that there actually is a problem with how the table's being filled out, which kind of blows. So when it's 0 and 1, that's set up here. I'm saying for every sparse table that just represents one dimension, like, fill it out. But for some reason it's not doing that properly. So I'm saying for every layer of the sparse table, look at every index, table at 0 at I, at L2 minus 1 at J, table at 0 at I at L2 minus 1 at J plus half the width. At 0 at I at L2 at J. Yeah, that seems right. Do I ever set the initial base case for the sparse table? That's exactly what this is. 0 at I, 0 at J. So I'm saying, ignoring any higher layer of sparse table, if you're just looking at this single coordinate, then that's this coordinate. It's like a tautology. Kind of makes me want to print a specific row from the table. So it's going to be sparse table at 0, at 2. I want to look at this final row at 1. Plus 3, I don't know. Or no, not sparse table, table. Or I'll just go up to like plus 10 to see what it says. A bunch of zeros, so it never filled it out. what about just at 0? Did it ever do this? No, I never filled this out. Oh, I see why, I see why. It's because I said n minus 2, m minus 2. Because as far as like the aggregate size of a square, that's what I care about. But I still need these corners. That's funny. Okay. That's not that bad. I could say for I, well, I could just say here, table at 0 at I at 0 at j equals x. And then that covers those. And then this should actually have values. Yeah, which is what I would expect to see. One, 1, 1, 2, 2. Looks pretty good. I have no real way of testing this. I guess I could just make a huge grid of 1s and 0s and like see if it freaks out. I mean, what do I even say though? I'll say vector, vector int. I'll have it be a 20 by 20. How do you do? Whatever, I don't care. I'm just gonna submit it. Let's see what happens. Damn, maybe there's a contest going on. Damn. Okay, these were like self-respecting test cases. So I said 1, 2. 2, 2, 4, 3. So 2, 2. 2, 3, 4, 3. There's no apparent reason why I would do that. 2, 2, 4, 3. I can definitely see this 2. One, 1, 3, 2. It says 1. So right here it should say 2. If it's looking at 1, 1 up to 2, 3, 2, it's saying both of these are a 2. Two, 2 up to 4, 3. Yeah. So why is it not seeing that? 3, 2. This is a size of 2. So that means that L1 and L2 are going to be 1 and 1. No. It's querying a 2 by 2. That doesn't mean the size that it is querying is a 2 by 2. 1 and 0 would be correct. So one of these should be a 2. Actually, both of these should be a 2. All of these should be a 2, but they're not. So that tells me up here, maybe somewhere I'm not filling it out correctly. Well, row 1, row 2, column 1, column 2 are all 1, which I don't think is right. Because if I'm looking at 2, 2, 4, 3, it should check this number, which is a 2, and this number, which is also a 2. So why would it not do that? Row 1 and row 2 should be 1 and 2. Column 1 and column 2 are fine as 1 and 1. So row 2, x2 minus that's not right. X2 should be 3. Okay, I see 3 minus 2 would be 1. What is it, minus that over 2 or something? Oh, no, this is right. It is querying. Row 1, row 2, column 1, and column 2. It only needs to make one query 4 times, but whatever. But the query itself is incorrect. Because all of these are 0, which should not at all be the case. At the very least, they should be 1, but they should really be 2. It's probably right here. L2 is equal to 1. There's no reason why L2 would not. I would not also need to look at L2 as 0. Okay, if that was it, that was pretty satisfying. One two one zero 1 1 1 1 1 2 1 2 1 0 1 1 1 1 2. That looks pretty good. One 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 two two. Was that what it originally was? Yeah. Hopefully it's not too slow. That'd be sad. Feels good. That was a needlessly complicated implementation of a 2D sparse table. I was definitely right to check that it was 512 megabytes in 5 seconds. Was the longest it took? 1.875. So if I didn't use a sparse table, if I used a segment tree, I think that would have like messed up. Because you would have had some sort of log of a million factor in there, and I think that would have messed it up. No, maybe not, because constructing is log of a million anyway. Let's see it. Let's see that boosted ass red coloring. Nice. Why don't you give contests? I think I have other priorities in life right now, and I'd like to do contests. Like, I want to do that. I think probably there's a lot of people in my shoes that it's like you want to see the number go up. And everybody, I guess before you do any contests, you're at 0. If this is your rating chart, I really want it to be like that, right? Instead of like that or something. So I guess I'd rather wait until I'm better, but I think that's actually not really the real reason. I think it's more just that I don't want to distract myself from the things going on in my life. Because I know myself, and I know that I'm very easily addicted to stuff like this. And I think the fact that I've been streaming for 2 hours is proof of that. All right, well, thanks for... Isn't that a good thing? I think it's a good thing if you harness it. So, like, I've realized, like, if I study for, like, the MCAT, yeah, that's extremely valuable. Like, that's, I guess, what separates people that do well from people that don't. But if it's 3 p.m. on a Monday and you're doing code forces, like, and with no intentions whatsoever of applying to a job that requires this, like, I guess that's definitionally not really going to lead to anything useful. Down the line, possibly. I don't know. I'm going to move in a year, and I'm kind of examining my options. I don't know if you saw that graph on Reddit that was like the number of tech jobs, and it's just like dropped off a cliff. So I'm like, okay, what other professions require you to like think a bunch, you know? I kind of want to see what they did. Calculate DP at IHJ is the maximum square ending in cell at IHJ. Okay. Binary search. Find some value. 2D sparse table. So it was exactly this. I don't think you'll face a problem with getting a tech job. Maybe. I don't know. I also just want to... Like, I know myself, and I actually absolutely can just sit and scratch my head over a puzzle for 6 hours straight, and I have done so on stream. But I think unless you're at an HFT, which I don't have the years of experience to really be applying to stuff like that, I think most tech jobs, you're not like doing 2D sparse tables. I think most tech jobs, it's like unit testing and stuff like that, is my understanding. Or at least like it's a desk job, of course. And just my temperament, I tend to do really well in like high stress environments, and I tend to seek those out, like really acute moment to moment life or death type of stress, rather than like get up at 6 every day and like get your grind on. Like, I'm not very good at that. I'd love to get good, but you gotta start somewhere. Wow, 383 people got this. I see what BetSimp was talking about. Like, I feel like I see a problem with 1200 solves, and I'm like, that's... Maybe it's different with Div 1, but I would not consider that a 2700 rated problem. I'd consider that like low 2000s. I also need to decide to become a party maker. I'm going to keep going for 5 more minutes. To train this for this role, she gathers all her owl friends in the country house. I see why so few people solve this. They're M chairs located, it's so cryptically written, located in a circle consequently numbered with integers 1 to m. Thus, chairs I and I plus 1 are neighboring for all I from 1 to m minus 1. Chairs 1 and m are also neighboring. Some chairs are occupied by our friends. There are n friends in total. No 2 friends occupy the same chair. The rules are as following. Each participant removes from the game the chair he is currently sitting on. Each of the participants chooses a direction she will follow, clockwise or counterclockwise. The direction may coincide or be different from any pair of owls. This seems like the kind of thing where you recognize that actually if 2 people pass through each other, that's the same thing as them. Like, it's 2 ships in the night, it doesn't matter, right? Each turn, all guests move 1 step in the chosen directions. If some guests move to the position with a chair there, they remove this chair. The game ends if no more chairs are left in the game. Owls are very busy and want to get rid of the game as soon as possible. They cooperate to pick the direction. Your goal is to find the minimum number O moves required to finish the game. Interesting. Why would you not just always have everybody evenly spaced going the same direction? That seems like the minimum possible amount of time it could take. So here, if there's 6 chairs, oh, they begin at a certain chair. I see. So you don't get to choose where they begin. So what you choose is which direction they go. I feel like I've seen this before. So you could do 1D DP. Yeah. You do 1D DP, that's a binary decision. You say, does this owl move to the left or does this owl move to the right? It would be 2D DP, really, because you would say the previous owl either moved to the left or the right. I guess it's not so simple because if the previous owl moved away from you, the owl before that could have moved towards you, or the owl before that. So it's going to be a variable cost. Maybe the answer to that is that you prove some greedy formulation that no 2 owls will ever travel in the same direction. Like maybe you could prove if this is your circle, everybody has their starting positions. But I don't even want to like formulate it that way. I think I just want to say like, if you have this and you say, okay, this guy's going this way, this guy's going this way, and you want to already be thinking about what the state is going to be up here, and you're here, I feel like you might be able to get away with a greedy formulation to say, always go this way. No, you can't say that. Prefix sum, I guess. What do you mean? Okay, I think it might be 3D DP, but really it's just 1D DP. And I think your state is going to be, and I'm not going to do this problem, but because this is The one I just did was 2700 rated, which is boosted because this was years ago. But this is a fourth that people solve this, so there's no way I'm going to solve this in the next like 5 or 10 minutes. So you have dp at I at j at k. That's at index I. It's going to be something like previous choice was j. 0th choice was k. Because when you get to the last one, you have to remember that this wraps around. So all of a sudden, it really matters what the first choice was. If the first choice was like you went forward, then you have this extra amount you have to do. But if the first choice was you went backward, then you have like half that or whatever it would be. I guess it would always be half rounding up, right? Something like that. Yeah, I think so. My whole greedy formulation thing here, I think it's not exactly correct, but I think it's close enough. And I think what you could say, okay, this is what it is. You could say you're at this index I, and I'm already thinking about index I plus 1 up here because I want to make the decision here. Do I go forward or do I go backward? And that's going to depend on here. I want to say, did my previous thing go forward? Because if my previous thing went forward, I have way less distance. So I'll just know like how long that takes. And that's going to take half the time roughly, as opposed to if this went backwards. Yeah. But the thing is, if this went backwards and this went backwards, like dp at j here, what I really want is to say index I, that's going to add n to my state space. J is just, well, the previous choice was you went forwards or backwards. That's times 2. And then K is the 0th thing went forwards or backwards. That's times 2. But the problem is if this went backwards and this went backwards and this went forwards, you're in a really weird scenario where like, well, maybe this doesn't meet halfway. It meets like there or something. And it depends on which previous index went forward. So then all of a sudden this becomes times n, and then it's O of n squared, and it doesn't work. So that's where I'm like, where's the greedy formulation, right? And I'm thinking like, can you decide that will never happen? And I think that will never happen because right here, when you're at index I, let's say, ignoring I plus 1, and you're seeing this went forwards, this went backwards. What if I tried going backwards? I think what you would say is, well, this is further from this than this was. So therefore the distance it took, the time it took, because all I care about is the minimum time for every gap to be closed, like however long that takes, whichever one took the longest is like the bottleneck, that's all I care about. So this gap close right here that took like half the time of their distance, you could say, well, that's not really relevant anymore because this could have just gone forward. And now this and this are the bottleneck. But then this is what's going to interact with this. Because at the point where you're saying this goes backwards, like there's almost no point to that. Is that true? I think the greedy formulation I'm toying around with is that it'll always be I went forward or some sort of predictable I minus 1 thing went forward. I don't think that's true though. I think that's actually easily disproven. If you had two things that were a distance of like this, then obviously like you would want this to go this way, this to go this way, and this to go this way. And then this would be your bottleneck. But this would not at all imply that this needs to go this way. And it doesn't matter what's past here. If there's something there, you would need to say this goes this way, I guess. But I guess it would get tricky because then you'd have this distance right here. And what's going to stretch that? It would have to be either this one or this one that eventually goes all the way around. I think that's actually the key here. Is that if you ever have a situation where this goes this way and this goes this way, no, that's wrong. No, is it wrong? I was gonna say, like, I feel like you could almost prove something about you start out and your result is at worst everything goes in one direction, in which case it's just going to be whatever the maximum distance is between everything. At worst, that's like that's the worst you can do. And I think you could use that fact to say, if you're ever knowingly going above that, then you know you're doing worse than the baseline, and therefore you can treat that as invalid. And you can use that as kind of a greedy formulation, perhaps. Side question, are you participating in Meta Cup? I don't know what that is, so I guess not. Is it like a Meta sponsored? I feel like I saw Meta Cup. I feel like I did a few Meta Cup questions a couple years ago. I'm probably not, because all of my Facebook accounts, all of my like 8 Facebook accounts have been banned except for one, and it's not my real name. I don't know why they were all banned, but... And now I can't make a new one because like my actual phone number is associated with a banned one, and all my burner numbers it recognizes as like not valid anymore. Oh, that was 2 days ago. That's cool. I don't know though. I was working through some of these problems, and these were like not the easiest. I forget. I did like the easiest one on some contest, and it like already had a weird trick I hadn't seen. And with this, it's like some Eastern European thing. And they're like, oh, if you're over 24, then we don't care. If you're not in high school, we don't care. I'm like, damn, okay. You really got to know your stuff, huh? That's the kind of thing where I'm like, I guess it's easy to like ask me, like, how do you get into Fang? You're doing these like crazy questions, which, to be fair, it's long ago when I think ELO was inflated. But I feel like there's people where I want to ask them that a lot. Like I still feel like I'm not really all that remarkable at this. I think I'm good enough to sound smart, but I don't think I'm good enough to like win competitions. And so at that point, I'll treat it like just personal enrichment and practice still, which sadly has to take a secondary place to my career and social life and stuff. I do feel like there's a greedy formulation to prove here. And I feel like it comes down to like if you have three things. If you chose for this to go this way, and this to go this way, and then you're here and you're deciding what to do. But really you're not here, you're here. That's what I care about. Sea of Autism, thanks for watching. If you're here, I just really feel like you could say almost like you would never want to go backwards unless you knew for a fact that that might take longer than this. And the only way it would take longer than this is if here, when you went backwards, you would just reach this before you reached this. So I think what I'm trying to illustrate is like, you were here, you went forwards, or you were at some previous thing and you went forwards, but I'm kind of doing a proof by induction a little bit. So you were here, you went forwards. You're here, you go backwards. I think what I'm trying to propose is that there's no way that this will ever reach this. You will always reach this point first, or else it wasn't optimal to begin with to go backwards, and that's provable. So you go forwards and then backwards. If this reached past this point, and that was relevant, I think this is the important part. If this reached past this point and that was relevant, yeah. I'm going to call these X1, X2, X3. So X1 went forward. If X1 surpassed X2 and that was a relevant choice, like then this is how long it took. And that was the halfway point between these. Then there was no point in going backwards here. You could have just gone forwards because you could have just spent this time doing this. Okay, that's what it is. So then for each dp at I at j at k, this is your current index. This is, did the previous thing go forwards, or do you need to exactly hit the previous thing itself? And then this is, did the first thing go forwards or backwards? Okay, I'm satisfied with that. I'm out. Thanks for watching. I don't know what that is.